If you look at the Cassini images of Phoebe, you see that it is a pretty heavily cratered surface. So it's been hit with things for billions of years, and material has been excavated and thrown into the space around Phoebe. The question is, where did all that material go? Where are all those dust particles? So we got the idea to use the Spitzer Space Telescope to try and look for dust in the region around Phoebe.
The Spitzer Space Telescope used infrared light, or heat signatures, to detect what's normally hidden from view.
If you were able to see how the Spitzer telescope sees, it would be like when you put on night vision goggles and all of a sudden you're able to see in the dark.
We got our images and they were extremely interesting.
Phoebe rides within a colossal ring about 10 million miles across, wrapped around Saturn.
It is the largest ring by far in the solar system.
This ring is so big that 1 billion Earths could fit inside the volume of the ring.
It makes perfect sense that this ring should be called the Phoebe ring because it is associated so closely with the moon Phoebe.
The Phoebe ring moves around Saturn in the same direction as its moon Phoebe, backwards from the other moons and rings. Each time a passing object or rocky debris gets too close to Phoebe, boom. The resulting impact throws dark material out into space.
So this dark material in this huge ring starts to fall in towards Saturn. And Iapetus is basically running through those particles in its orbit.
How Iapetus orbits Saturn is key to solving the mystery of why it has these black and white halves.
So Iapetus, like our moon that orbits the Earth, is tidally locked, which means one side of Iapetus always faces Saturn, the other side always faces away from Saturn. Imagine this snowball is a freshly formed Iapetus, completely uniform in its brightness on all sides. Now, as it orbits around Saturn through the Phoebe ring, it will pick up dark dust particles from that ring. And because it is tidally locked to Saturn, the same hemisphere will keep piling on dust every time it goes around for millions and millions of years, continuously darkening this side of Iapetus.
As soon as the front side of Iapetus became darkened, the ice underneath started heating up more quickly. So that would become a gas and migrate around to the colder, lighter side of Iapetus.
The ice vaporizes from the darker, warmer side and refreezes onto the colder, lighter side.
And so this means over time, the dark side becomes darker, the light side becomes lighter.
It's a slow process, one dust particle at a time. But it's the best explanation of how this peculiar moon got its self-sustaining, warm, dark face.
Iapetus just shows us the potential of the interconnectedness between the planetary bodies in our solar system. We think they're isolated, but nothing's isolated.
Iapetus is not the only icy moon affected by the system it exists within. Another moon, closer to the sun, reveals not only a unique connection with its neighbor, but also hints that something potentially profound could lurk beneath its surface.
T-minus 5, 4, 3, 2, 1. Ignition and liftoff. Atlas V with Juno on a trek to Jupiter.
The Juno mission is to investigate the origin and evolution of the gas giant Jupiter. largest planet in our solar system.
The main goal of the Juno spacecraft is to study Jupiter. However, as it orbits Jupiter, it's taking these wonderful images of Jupiter's largest moons.
Ganymede, the largest moon in the solar system. Io, the most volcanically active. And then there's the icy moon, Europa, the odd one out with the smoothest surface. It's an ancient moon, billions of years old, and yet mysteriously has a young surface with few craters.
We can get an idea of how old the planetary surface is by counting the number of impact craters. Europa barely has any impact craters, which means that its surface must be really young.
And that's not all that makes Europa different. It's crisscrossed by a strange network of striking red lines.
The surface of Europa has a lot of interesting cracks and features to it, and has lots of lines which look almost like a network of blood vessels in an eye.
These lines are vast ice cracks, some of which are 15 miles wide, with a dark red floor.
What could be creating these crisscrossing lines and patterns on Europa's surface?
The canyons on Europa are so significant that NASA's planning a mission to go to Europa to explore them.
And in preparation, scientists are exploring similar environments on Earth, like these icy terrains in Alaska.
I think many of the most important questions in planetary science can be addressed by going to worlds like Europa.
NASA scientist Sam Howell is studying what may be at the heart of Europa's mysterious appearance.
What I'm most excited about, coming from a background in studying plate tectonics here on Earth, we see systems of rigid icy plates moving around similar to the way Earth's plate tectonics looks on the surface. But digging in, we expect those processes to be very different.
Europa's surface features indicate they are a result of tectonic activity.
This is an up-close image of Europa's surface, and you can see this large, dark red band in the very center of the image.
We know that this feature is created due to tectonic activity because it appears that the crust of Europa has pulled apart and you've had material flow up from underneath. But if we were to take this feature and extract it from this image, both sides of the crust would fit back together like a puzzle piece.
We did not expect to see tectonic activity on a tiny moon like this, but there it is.
So far, this kind of global tectonic activity has only been observed on Earth.
Take a look at Earth, and you'll see that South America looks like it fits right neatly in there into Africa. And so we know that in the Atlantic, the seafloor is spreading, and that's what spread those two features apart.
On Earth, the rocky crust is broken into plates. They move as softer rock beneath flows very slowly over geologic time.
Europa does not have molten rock like Earth does, but what we do believe Europa has is a subsurface ocean.
A vast body of liquid water that exists underneath its icy surface.
There is more water in Europa's subsurface than all of Earth's oceans, rivers, and lakes.
This massive ocean sits beneath a layer of water ice, which could be up to 15 miles thick in places. So what force is powerful enough to crack Europa's extensive icy shell?
As Europa and all of the other large moons orbit Jupiter and interact with it, they are all constantly pushing and pulling and tugging on each other. And this process is called tidal heating.
The tidal heating varies depending on how close or far Europa is from Jupiter and the other moons, resulting in temperature changes in the ocean.
And as the temperature of the ocean changes, the ice shell thickens and thins and expands and contracts.
The mechanics of which can be seen on Earth.
As water freezes, it takes up more space and expands into ice. It's very similar to if we were to take a bottle of water and place it into the freezer. First it would expand, and then we'd notice a large bit of cracking. This is what is happening on Europa.
Scaled up to the size of a moon, these ice expansion cracks create massive canyons across Europa. As these canyons form, a key ingredient from the ocean below surges up through the cracks, giving Europa's markings their distinctive red.
So the red marks that we see on Europa's surface, these cracks and lines, are salts that have come up from below the surface.
Suggesting a tantalizing possibility. This crisscrossing system of salty canyons means we might find life in the ocean underneath Europa's icy shell.
Life as we know it needs three basic things: water, a source of energy, and also essential elements.
Europa has an ocean and a source of energy from tidal movements. But it's missing the final key ingredient, some essential elements. However, with a little help from its neighboring moon Io, these elements can be found on Europa.
Io is an extremely volcanically active place, and these volcanoes emit sulfur and other sulfur products. And these make it all the way onto Europa. And sulfur is one of those essential elements that life on Earth uses. All of the sulfur that's coming from Io and landing on Europa's surface is interacting with the salts and water that's coming up from underneath Europa's icy crust.
Chemical reactions between the sulfur from Io and the salts on Europa create essential molecules needed for life.
And this allows for this perfect breeding ground for potential life to form and evolve.
Europa is such a strong candidate for life that NASA is already preparing to explore the moon. The goal is to study Europa's surface in more detail so that a future mission can one day land and explore beneath its icy crust. And scientists like Sam are already testing ideas for studying Europa's watery world.
What we're doing is we're deploying a robotic probe into the ice and under it to explore what this lake environment is like. We might have the opportunity in my own lifetime to answer a question that's intrinsic to all of us. Are we alone in our universe? Are we alone in our solar system? And one of the most exciting aspects of exploring Europa is the potential of someday knowing whether or not there's life in our own solar system.
Europa is one of the last ice moons that can exist this close to the sun. Worlds existing any closer to the warmth of the sun like the rocky worlds of Mars, Earth, and our moon, have relatively little ice because they lie inside what is known as the ice line.
You can't see the ice line, but you can see its effects.
When small bodies that are primarily composed of ice cross inside of the ice line, the ice within them begins to vaporize.
Sometimes icy rocks are ejected from the frigid outer regions of the solar system and pulled towards the sun. These are known as comets.
Comets are basically dirty snowballs, mostly water ice with a little bit of dust. And as they come into the inner solar system, they get heated up by the sun.
As comets cross this invisible ice line, their ice starts turning into gas.
And that's what forms these long tails that we can see when you look at a comet. And those tails stream away from the sun as the comet moves in towards it.
Inside the ice line, ice is rare, but there are places where it can hang on.
Mars is within the ice line of the solar system, but it still has ice in it and on it.
It's the end of winter, and it's been dark at Mars's south pole for over 150 Martian days straight. Mars holds on to much of its ice at its poles. The ice sheet here is not like any on Earth, because as winter turns to spring, the surface becomes covered in strange features. And with the launch of the Mars Reconnaissance Orbiter in 2005, we began to see them like never before.
The Mars Reconnaissance Orbiter is a satellite of Mars that takes photograph after photograph of Mars' surface, and so it's able to see these things come and go and change with the seasons.
The images show dark fans on the surface, meaning something must have risen into the air above them.
We see these features and they will go in the direction depending on the wind pattern of Mars. So we know the material is being pushed out from underneath.
This phenomenon seen on Mars depends on the type of ice that falls from the Martian skies. During winter at the South Pole, more and more snow falls. But with so little water in Mars's atmosphere, this isn't the type of snow we have on Earth. This is carbon dioxide snow.
Every winter, 3 to 4 trillion tons of carbon dioxide snow falls on Mars. That's so much snow that the atmospheric pressure at the surface of Mars decreases by about a third.
The air is literally freezing to the ground, forming carbon dioxide ice caps at the poles. But in spring, as the warmth of the sun reaches the poles again, something incredible happens.
As the sun comes over the horizon, the carbon dioxide ice is heated.
This carbon dioxide ice can turn to gas, and when it does, it forms these geysers that also bring other material from the subsurface to the surface.
And depending on which way the wind is blowing, it'll form these nice looking fan features.
Because of Mars's combination of atmospheric pressure and temperature, the carbon dioxide turns from ice to gas without passing through the liquid phase.
On Mars, its atmosphere actually falls onto the surface and then vaporizes back into the atmosphere on an annual basis. That's absolutely wild because it's so different from what's happening here on Earth.
These conditions on Mars have enabled carbon dioxide snow to create unique features on its surface. But the conditions found on its nearest neighbor, close enough to see from Mars with the naked eye, have allowed for something extraordinary to form. And just like Mars, Earth too has ice caps at its poles. But the similarities end there.
Earth's ice is really unique because we operate a very small temperature range and a very small pressure range on the surface. The ice that we experience is a very small subset of the total ice that's in our universe.
Earth's temperature and pressure ranges allow water to exist in all three states: solid, liquid, and gas.